please subscribe to support the channel. Humanity has achieved incredible things in space, landing on the moon, exploring Mars, and sending probes to the edge of our solar system. Yet traveling to distant places like Pluto or Proxima Centauri remains far beyond our reach. These journeys aren't limited by imagination, but by the unyielding laws of physics. The distances involved are staggering, the energy requirements astronomical, and the timescales almost incomprehensible. Even with our most advanced spacecraft, reaching Pluto takes nearly a decade, and getting to Proxima Centauri would take tens of thousands of years. Despite our technological brilliance, we are still cosmic beginners, bound to our solar neighborhood, but understanding these limits is what fuels our drive to keep exploring and one day make the impossible possible. Now that we've set the stage for why journeys to distant worlds push against the limits of what humanity can achieve, it's important to understand exactly where these destinations lie. When we speak of Pluto and Proxima Centauri, we're talking about two vastly different kinds of frontiers. One still within the gravitational embrace of our sun, and the other far, far beyond it. Pluto sits on the outer edge of our solar system, orbiting in a region known as the Kuiper Belt, a vast ring of icy bodies, remnants from the formation of our solar system more than 4.5 billion years ago. Once considered the ninth planet, Pluto was reclassified as a dwarf planet in 2006, not because it lost its significance, but because astronomers recognized it as part of a broader family of similar icy worlds. It orbits the Sun at an average distance of about 5.9 billion kilometers, roughly 39 astronomical units, with 1 AU being the distance from the Earth to the Sun. Even at that immense distance, Pluto is still, cosmically speaking, in our backyard. It's a member of our solar family circling the same star that warms our world. But beyond that boundary, however, lies a realm so vast it defies easy comprehension. Once you leave the Kuiper Belt, you enter the interstellar void, a gulf of near-empty space stretching billions of kilometers before you reach even the closest neighboring star. And that star is Proxima Centauri, part of the Alpha Centauri system, located about 4.24 light-years away from Earth. In more familiar terms, that's roughly 40 trillion kilometers, so distant that even a beam of light traveling at the ultimate cosmic speed limit of 300,000 kilometers per second takes more than 4 years to get there. Now, Proxima Centauri may sound impossibly far away, but in cosmic terms, it's still right next door. Our solar system extends far beyond Pluto, past the Kuiper Belt, through the scattered disk, and out to the mysterious Oort cloud, a distant shell of icy debris that may stretch up to 100,000 astronomical units from the Sun. And beyond that, interstellar space, the dark ocean separating our Sun from other stars. That's where Proxima Centauri comes in. It lies at a distance of about 4.24 light-years, which translates to roughly 268,000 astronomical units, or nearly 40 trillion kilometers. To put that in perspective, if the Sun were the size of a coin sitting in the middle of a football field, Pluto would be about 40 meters away, and Proxima Centauri would be another coin sitting more than 10,000 kilometers away, roughly the distance between New York and Cape Town. The space between our solar system and the nearest star is not just empty, it's almost inconceivably vast, filled with diffuse gas, cosmic rays, and dust particles that drift across the interstellar medium. These distances are so immense that even our language strains to describe them. A light year, the distance light travels in a single year, equals nearly 9.46 trillion kilometers. The fastest spacecraft humanity has ever built, Voyager 1, launched in 1977, has traveled for nearly 5 decades and is only about 24 billion kilometers from Earth. That's less than 1,000th of the way to Proxima Centauri. At its current speed, it would take over 70,000 years to reach the nearest star. That's the scale we're talking about, a scale so immense that it transcends anything we can directly experience. Even the smallest sliver of interstellar distance makes the span between Earth and Pluto look like a short drive. These cosmic gulfs remind us how tiny our world really is, a small blue dot circling an ordinary star in a galaxy of hundreds of billions more. Understanding these distances isn't just about appreciating big numbers, it's about realizing how the very structure of the universe sets natural boundaries around our reach. The farther we look, the more we see that space itself is the ultimate barrier. Not because it resists us physically, but because its scale renders time and energy almost meaningless on human terms. And this brings us naturally to the next challenge: time. Specifically, how long it would actually take to reach these distant destinations, even with the fastest spacecrafts we have today. Because distance alone doesn't tell the full story. It's when you compare that distance with the speeds we can actually achieve that the true magnitude of the problem becomes clear. When we talk about the travel times involved in reaching places like Pluto and Proxima Centauri, we begin to see just how profoundly distance shapes our perception of the universe. We can measure distances in kilometers, astronomical units, or light years, but it's only when we translate those numbers into time that the challenge of space travel truly hits home. Time transforms cold statistics into a reality we can understand. After all, 1 billion kilometers doesn't sound much until you realize it might take a spacecraft nearly a decade to cross it. And a light year, a distance so vast it defies imagination, becomes tangible only when we admit that even our fastest machines would need tens of millennia to cover it. Let's begin with Pluto, the distant dwarf planet on the outer rim of our solar system. For decades, Pluto was little more than a blurry dot through our most powerful telescopes. Then, in January 2006, NASA launched the New Horizons spacecraft, a robotic probe designed to change that forever. New Horizons was the fastest spacecraft ever launched from Earth at the time. Its launch speed relative to Earth was an incredible 58,000 kilometers per hour, about 36,000 miles per hour. Enough to pass the Moon in just 9 hours and speed past Jupiter in a single year. Even so, it took 9.5 years for New Horizons to reach Pluto. Think about that. Nearly a decade of travel at a speed faster than any human-made object before it, just to perform a quick flyby of a world still orbiting our sun. The probe couldn't slow down to orbit or land. Doing so would have required an enormous amount of additional fuel. Instead, it zipped past Pluto in July 2015, capturing breathtaking images and a treasure trove of data in a matter of hours before continuing onward into the Kuiper Belt. From Earth's perspective, that brief moment represented almost 10 years of effort, planning, and waiting. And yet it was only a glimpse, a single passing handshake with one of the solar system's most distant members. This timescale might not sound unreasonable when compared to the decades-long ambitions of deep space exploration, but it underscores a sobering truth. Even at extraordinary speeds, space is vast beyond measure. And Pluto, despite its reputation as a far-off world, is still local. If reaching Pluto requires nearly a decade, what would it take to reach the nearest star beyond our sun? That's where Proxima Centauri enters the conversation, and where the concept of long journey takes on an entirely different meaning. Proxima Centauri lies 4.24 light-years away, or about 40 trillion kilometers from Earth. To appreciate that distance, imagine taking the speed of New Horizons, 58,000 kilometers per hour, and stretching it across those trillions of kilometers. At that velocity, it would take roughly 75,000 years to arrive at Proxima Centauri. 75 millennia! That's longer than the span of all recorded human history. When our ancient ancestors were carving tools from stone and painting on cave walls, a probe launched then, at New Horizons speed, would still be only halfway to Proxima Centauri today. Even the Voyager 1 spacecraft, humanity's most distant emissary, launched in 1977 and currently moving at about 61,000 kilometers per hour, would need about 73,000 years to reach the nearest star system. To put that in perspective, by the time such a spacecraft arrived, every trace of modern civilization would have changed: languages, nations, and perhaps even our species itself. Some might suggest building faster craft. Let's imagine something traveling 10 times faster than Voyager 1, say 600,000 kilometers per hour. Even then, the journey to Proxima Centauri would still last more than 7,000 years. Increase the speed 100-fold, 6 million kilometers per hour, and you're still looking at over 700 years of travel. To reach Proxima Centauri in a single human lifetime, a spacecraft would need to travel at about 10% of the speed of light, or roughly 30,000 kilometers per second. That's a speed more than 500 times faster than New Horizons, and achieving it would demand technologies and energies far beyond anything our civilization can currently produce. There are a few ongoing research concepts that try to close that gap. One of the most ambitious is the Breakthrough Starshot Initiative, which proposes sending microscopic spacecraft propelled by powerful Earth-based lasers attached to ultra-thin light sails. In theory, these craft could reach 20% of the speed of light, making a trip to Proxima Centauri possible in just over 20 years. But in theory is the key phrase here. The technology required, gigawatt-level laser arrays, perfectly reflective sails, and the ability to survive the violent acceleration process remains far beyond our engineering capabilities. Even if it became possible, those tiny probes wouldn't be able to slow down, carry instruments, or communicate easily once they arrived. So when we compare the travel times to Pluto and Proxima Centauri, we're really comparing two different categories of impossibility. Pluto represents the edge of what we can reach, a destination that requires patience, precision, and years of travel, but one that lies within our technological horizon. Proxima Centauri, on the other hand, represents the vast beyond, a place that mocks our ingenuity with distances so great that even light, the universe's ultimate speed limit, seems slow across them. And it's not just about the journey time itself. Every extra year of travel adds new problems: maintaining power, protecting equipment from radiation, preventing micrometeoroid damage, and simply keeping a spacecraft functioning over decades or centuries. The farther we go, the more time becomes an enemy, eroding technology and increasing the odds of failure long before the destination is ever reached. When viewed through this lens, the gulf between Pluto and Proxima Centauri becomes almost philosophical. One is an engineering challenge. The other is a challenge of time and physics themselves. The difference between a decade and 70,000 years isn't just numerical, it's existential. It defines what kind of species we are right now, bound to the inner sanctum of our solar system, and what kind of species we would need to become to even attempt a journey between the stars. And underlying all of this is a deeper limitation, a rule woven into the very fabric of the cosmos that no matter how hard we try, nothing with mass can exceed a certain speed. It's not just difficult, it's forbidden. That brings us to the next critical concept in understanding why journeys to Pluto, and especially to Proxima Centauri, remain so staggeringly difficult. The cosmic speed limit, the speed of light. Every journey through space, whether it's a trip to the moon or a theoretical voyage to another star, is governed by one unbreakable law: the speed of light. This is not just a fast number we throw around in science fiction. It is the fundamental speed limit of the universe, the maximum velocity at which information, energy, or matter can travel through space. No matter how powerful our rockets become, no matter how advanced our technology evolves, this limit stands as an absolute wall in physics, a line that no object with mass can ever cross. Understanding this boundary is essential to understanding why journeys to Pluto, and especially to Proxima Centauri, remain so staggeringly difficult. Light travels at about 299,792 kilometers per second, or roughly 186,000 miles per second. At that speed, light can circle the Earth more than 7 times in a single second. It is almost impossible for the human mind to truly comprehend how fast that is. And yet, when you consider the distances between stars, even light itself begins to feel slow. Light from the sun takes about 8 minutes and 20 seconds to reach Earth, more than 5.5 hours to reach Pluto, and a full 4.24 years to reach Proxima Centauri. That means when astronomers look at our nearest stellar neighbor, they're not seeing it as it is now, but as it was 4 years ago. We are in a sense always looking into the past. Now, why can't anything with mass reach this speed? The answer lies in Einstein's theory of relativity, one of the most profound and experimentally verified insights in all of physics. According to relativity, as an object with mass accelerates, its kinetic energy, the energy of motion, increases. But that energy doesn't just make the object move faster, it also increases its relativistic mass, or more precisely, the amount of energy that must be pushed to continue accelerating. The faster you go, the more energy it takes to go even faster. At everyday speeds, this effect is negligible. It doesn't matter when you drive a car or fly in a plane. But when you approach a significant fraction of the speed of light, it becomes enormous. For instance, at 90% of the speed of light, the mass of an object effectively doubles. From the perspective of an outside observer, meaning it takes twice as much energy to continue accelerating. At 99% of the speed of light, its mass increases more than sevenfold. By the time you reach 99.99999% of light speed, the energy required to accelerate even a small spacecraft approaches infinity. And infinity in physics means impossibility. That's why nothing with mass can ever reach the speed of light. Photons, the particles that make up light, can travel at that ultimate speed only because they have no rest mass. They are pure energy, not matter. Everything else, atoms, molecules, spacecraft, even the smallest particle with measurable mass, must forever remain below that cosmic ceiling. To see how unforgiving this limit is, consider this. The most powerful rocket engines humanity has ever built can push a spacecraft to perhaps 70 kilometers per second, or about 0.023% of the speed of light. Even theoretical propulsion systems, like nuclear fusion drives or antimatter engines, might, at best, reach 10 to 20% of light speed in ideal scenarios. That sounds incredible until you realize that even at 10% of light speed, a trip to Proxima Centauri would still take over 40 years. And that's ignoring the staggering amounts of energy needed just to accelerate and then decelerate the craft. If somehow a human-piloted ship tried to reach that velocity, every tiny grain of interstellar dust in its path would become a deadly projectile, slamming into the hull with the force of high explosives. At near-light speeds, the universe itself becomes dangerous. Radiation, drag from interstellar particles, and even the faint wisps of gas that fill the void would pose catastrophic risks. The speed of light doesn't just limit our travel. It also defines the structure of time and space. According to relativity, the closer you get to light speed, the slower time passes for you relative to a stationary observer. This phenomenon, known as time dilation, means that a traveler moving near light speed would experience a shorter journey than people remaining on Earth. However, from Earth perspective, the trip would still take the same objective time. So even if travelers to Proxima Centauri experience the journey as a few years, thousands of years could pass back home. A bittersweet trick of physics that doesn't solve the practical problem of interstellar travel, but rather deepens its philosophical mystery. And this brings us to an even deeper realization. The universe enforces its limits not out of malice, but out of consistency. The speed of light is not a speed we could break with a better engine. It's a foundational constant that maintains the stability of everything, from atomic particles to galaxies. Without that limit, the laws of cause and effect, the very logic of the cosmos, would collapse. Information could travel backward in time, events could influence their own causes, and the universe as we know it would unravel. Science fiction often imagines faster-than-light travel, warp drives, hyperspace jumps, wormholes, and while these ideas are fascinating to explore, they remain speculative. Some theories, like the Alcubierre drive, suggest that if space itself could be expanded behind the ship and contracted in front of it, the craft might effectively ride a wave faster than light without violating relativity. But the energy required for such a feat would exceed the total energy of entire stars, and it would require negative energy, something not proven to exist in usable form. So the cosmic speed limit is not just an inconvenience. It is a fundamental boundary that defines our place in the universe. It's a reminder that no matter how advanced our technology becomes, we're still bound by the same physical rules that govern everything, from the smallest atom to the largest galaxy. In the context of our journey, this law tells us something profound. It's not just the vast distances to Pluto or Proxima Centauri that hold us back. It's the fact that there is no shortcut through space or time. The universe is not built for quick travel between stars. It's built for patience, endurance, and awe. Yet even if we can never reach or exceed the speed of light, we might still dream of approaching it. And that leads us to another equally imposing barrier: the energy required to even get close to that speed. The problem isn't just physics, it's power. The amount of energy needed to push a spacecraft to a meaningful fraction of light speed is beyond comprehension, rivaling the total output of entire nations or even stars themselves. If the speed of light stands as the universe's ultimate speed limit, then energy is the price of trying to approach it. And that price is unimaginably, almost absurdly high. When people imagine building faster spacecraft, they often think of adding bigger engines or better fuel, as if the challenge were a matter of engineering skill. But in reality, the obstacle is far more fundamental. The amount of energy needed to accelerate even a small object to a meaningful fraction of light speed increases exponentially with velocity. The faster you go, the more energy you need, and the closer you get to light speed, the more that requirement spirals toward infinity.
Let's start with something concrete. Consider a small spacecraft weighing just 1,000 kilograms, about the size of a compact car. If we wanted to accelerate that modest vehicle to 10% of the speed of light, that's 30,000 kilometers per second, how much energy would we need? Using Einstein's famous relation, E equals 1/2 mv squared for non-relativistic speeds, and the relativistic equation as we approach higher fractions of light, the energy required would be roughly 4.5 times 10 to the 17th joules. That's equivalent to the energy released by about 100 megatons of TNT, more than the yield of the largest nuclear bomb ever detonated on Earth, the Soviet Tsar Bomba, which exploded with a power of around 50 megatons. And remember, that's just for 10% of light speed, barely scratching the surface of the relativistic regime. If you wanted to reach 50% of the speed of light, the energy requirements increase by a factor of tens, reaching on the order of 10 to the 19th joules. For context, that's roughly the total energy consumption of all human civilization for an entire year. Push a bit further, toward 90% of light speed, and the energy required becomes so astronomical that it rivals the total annual energy output of the sun. And that's for one small unmanned craft. If you imagine sending a larger crewed spacecraft with shielding, life support, and fuel, easily weighing hundreds of thousands of kilograms, the energy demands become cosmic in scale. The issue isn't just that our rockets aren't powerful enough. It's that our entire species doesn't currently have access to that much energy, even collectively. Every watt of electricity generated on Earth in an entire year wouldn't be enough to push even a tiny probe to a significant fraction of light speed. To put this into perspective, consider our most advanced propulsion systems today. A chemical rocket, like those used to launch missions such as Apollo or Artemis, releases around 10 million joules of energy per kilogram of fuel. That's impressive by everyday standards, but it's laughably small compared to the relativistic energies needed for interstellar travel. Even nuclear fusion, the process that powers the sun and the dream behind future starships, releases around 100 times more energy per kilogram than chemical fuel. Still not remotely enough for lightspeed travel on any reasonable scale. Suppose, optimistically, that we could somehow capture and store the energy equivalent of annihilating matter and antimatter, the most efficient energy conversion known to physics, where 100% of the mass is converted into pure energy via E equals mc squared. Even then, to accelerate that same 1,000 kilogram spacecraft to half the speed of light, you need to annihilate about 50 kilograms of matter and 50 kilograms of antimatter. That might not sound like much, but producing and storing even a few milligrams of antimatter is a staggering challenge. Current technology can create only nanograms of antimatter per year, at a cost of billions of dollars per microgram. The antimatter required to power a single near-light-speed probe would cost more than the global economy could ever produce, and storing it safely without catastrophic annihilation is another unsolved problem entirely. Even if we ignore cost and technology, there's still a deeper issue: efficiency. Rockets, by their nature, must carry their own fuel. To accelerate forward, they must eject mass backward, and the more energy you want, the more fuel you need to carry. But that fuel itself has mass, which in turn requires more energy to accelerate, creating a vicious cycle. For interstellar travel, this becomes a nightmare of exponential returns, the so-called tyranny of the rocket equation. If you wanted to accelerate to near light speed, you would need to bring an impossible amount of propellant, enough to outweigh entire planets just to move a small payload. This is why scientists have begun to look beyond rockets altogether. Some propose laser propulsion, where massive arrays of ground-based or orbital lasers push a spacecraft equipped with a reflective sail, avoiding the need to carry fuel. Others imagine fusion pulse propulsion, where small thermonuclear explosions drive a ship forward, or even antimatter drives that convert pure energy into thrust. These ideas are fascinating, but all of them face staggering technical and energetic barriers. Even with perfect efficiency, which no real system achieves, the power generation required would dwarf any energy infrastructure humanity has ever built. For instance, to accelerate a 1-ton craft to 20% of light speed in just a few minutes using a laser sail, you need a continuous laser array producing around 100 terawatts of power. That's about 5,000 times the total electricity consumption of the entire Earth at any given moment. And that's not counting the engineering challenge of building and maintaining a laser array the size of a continent, perfectly synchronized to focus light on a fragile kilometer-wide sail millions of kilometers away. Even if such a feat were possible, the problem doesn't end there. The craft would still need to slow down when it reached its destination, and that deceleration would require an equal and opposite amount of energy. In space, there are no brakes, no friction, no atmosphere to slow you down. If you can't burn enough energy to stop, your spacecraft will just hurtle past its target at a deadly velocity, just like New Horizons did at Pluto. Except now you're flying past another star system after a journey lasting centuries or millennia.
These unimaginable energy requirements expose a fundamental truth about interstellar travel. It isn't just a matter of going faster. It's about redefining what's possible within the bounds of energy, matter, and physics. Every fraction of light speed gained demands exponentially more power, and every improvement in propulsion technology faces the same universal bottleneck: the need to find, store, and use energy on a scale that rivals stars. And yet, this same obstacle, this unyielding energy barrier, is also what makes the dream so profound. It forces humanity to think bigger, to imagine technologies that don't yet exist, and to confront our limitations with humility. Perhaps one day, with advances in fusion power, matter-antimatter reactions, or energy collection on a solar system scale, we might narrow that gap. But as of today, even the smallest step toward the stars demands more energy than we can currently produce. Still, even if we could somehow solve the problem of energy, if we could generate that much power, there's another equally daunting issue waiting just behind it: fuel. Because having the energy isn't enough, you also need a way to store and use it effectively. And carrying enough fuel for a journey that might last thousands of years presents its own impossible set of challenges. Energy is only half the story. Even if humanity somehow found a way to generate the near-star level power needed to reach a meaningful fraction of light speed, the next question would immediately stop us cold. Where would we put the fuel? Every form of propulsion we know depends on mass being thrown out of the back of a spacecraft to push it forward. That expelled mass, the reaction mass, is both the engine's strength and its curse. Because in the vacuum of space, there's nothing to push against. Every ounce of momentum must come from ejecting something in the opposite direction. The faster and farther you want to go, the more propellant you must bring, and the heavier your ship becomes. The heavier the ship, the more fuel you need just to move that fuel. A feedback loop that grows exponentially until it crushes even the most optimistic mission plan. This problem is formalized in what rocket scientists call Tchaikovsky's rocket equation, one of the simplest and most unforgiving formulas in all of engineering. It links a spacecraft's velocity change, delta V, to the exhaust speed of its propellant and to the ratio between the ship's full mass at launch and its mass after burning all its fuel. The math makes the situation painfully clear. To double your final speed, you must square the fuel mass. To triple it, you cube it. Very quickly, the mass required fuel balloons into numbers larger than planets. For a sense of scale, take the Saturn V rocket, the most powerful launch vehicle ever used to carry humans. At liftoff, more than 90% of its total mass was fuel, and all of that energy was burned in just a few minutes merely to reach Earth orbit, a velocity of 28,000 kilometers per hour, less than 0.003% of the speed of light. To accelerate to even 1/10 of 1% of light speed, a spacecraft relying on chemical rockets would need to be almost entirely fuel, with only a microscopic fraction left for payload, instruments, and crew. In practice, it's impossible. Nuclear propulsion ideas improve the efficiency somewhat, but even they fall under the same mathematical tyranny. A nuclear thermal rocket, which uses a reactor to heat hydrogen and expel it as exhaust, might reach specific impulses several times better than chemical engines. That could shave years off a trip to Mars, perhaps even to the outer planets. But interstellar travel? It barely makes a dent. To reach 10% of light speed using a fusion or fission drive, the ship's fuel mass would outweigh Earth's largest supertankers. You need entire moons mined and processed just to fill the tanks. The picture grows bleaker when you remember that space travel isn't just about speeding up, it's also about slowing down. Once you arrive near your destination, you can't simply slam on the brakes. You must burn roughly the same amount of fuel you used to accelerate in the opposite direction. Unless your destination has a convenient atmosphere to aerobrake in, and neither Pluto nor Proxima Centauri space does, you must carry double the propellant, one batch for each half of the trip. In interstellar terms, that means doubling the impossible. A common misconception is that you could just refuel on the way, scooping up interstellar hydrogen with giant electromagnetic funnels, a concept called the Buzzard ramjet. It's an elegant idea in theory. A craft races through space, collects hydrogen, compresses it, and uses it for fusion propulsion. But the interstellar medium is unbelievably thin, containing just a few atoms per cubic centimeter. At realistic speeds, the energy needed to capture and compress that sparse gas far exceeds the energy you'd get from burning it. The faster the ship goes, the harder it becomes to scoop anything up. The Buzzard ramjet, once hailed as the perfect interstellar engine, turns out to be more of a poetic metaphor than a workable design. Even if we turn to the most efficient energy source imaginable, matter-antimatter annihilation, fuel storage itself would still be a showstopper. Antimatter must be kept from touching any normal matter, including the walls of its own container, or it will instantly annihilate. That means suspending it magnetically in a vacuum and preventing the slightest leak for decades or centuries. A single containment failure would release energy equivalent to a major nuclear detonation. No material or magnetic system known to science can guarantee that kind of stability for the timescales an interstellar voyage demands. And so far, every solution that tries to eliminate fuel storage altogether leads back to enormous infrastructure problems. Laser-driven light sails, for instance, would leave the heavy energy source back home, Earth, or perhaps a lunar power array, and push an ultralight craft forward with photon pressure. But even that approach has limits. Once the spacecraft is billions of kilometers away, the beam begins to spread out, losing intensity. Keeping the sail illuminated over light years would require laser arrays kilometers wide, perfectly aimed and coordinated across unimaginable distances. And again, once the craft reaches its target, there's no way to slow down without a matching laser waiting in that distant star system to push in the opposite direction. The inescapable conclusion is that fuel, not courage, confines us to the solar system. Every form of propulsion we can currently build, chemical, ion, nuclear, or speculative antimatter fuel, runs headlong into either the rocket equation or the limits of energy storage. Even if energy were free, we would still need to carry or transmit it somehow. And that logistical burden is what keeps Pluto a 9-year trip, and Proxima Centauri a 70,000-year dream. This constraint defines the character of our exploration. We send small, efficient probes like Voyager and New Horizons not because we lack imagination, but because physics demands humility. Those spacecraft coast silently through the dark on borrowed momentum, sipping the last traces of their onboard fuel only to make tiny course corrections. Each one is a monument to compromise, a balance between the thirst for speed and the limits of mass. Understanding the fuel problem leads naturally into another strange, beautiful twist of relativity, one that at first seems like an escape clause, but ultimately reminds us just how deeply time and motion are intertwined. If we could ever reach near light speeds, the clocks on board our ship would tick more slowly than those on Earth. To the travelers, the journey might feel short. To everyone else, it would span centuries. This phenomenon, called time dilation, is our next doorway into understanding the impossibility and the allure of reaching the stars. When we talk about traveling close to the speed of light, one of the most fascinating and counterintuitive consequences of Einstein's theory of relativity begins to dominate the discussion: time dilation. It's one of those ideas that sounds like science fiction, but is an absolutely real and experimentally verified aspect of our universe. In simple terms, the faster you move through space, the slower time passes for you relative to someone who remains still. It's not just a matter of perception, it's a physical, measurable effect. And while it might sound like a potential loophole for interstellar travel, time dilation offers only a partial escape. It can shorten the journey for the traveler, but it does nothing to shorten the wait for those left behind on Earth. To understand this phenomenon, imagine two identical twins. One stays on Earth, while the other boards a spacecraft capable of traveling at 90% of the speed of light. According to Einstein's special relativity, time on the moving spacecraft slows down compared to time on Earth. That means when the traveling twin eventually returns, less time will have passed for them than for their sibling. This thought experiment, known as the twin paradox, has been confirmed by countless real-world tests, from atomic clocks flown on airplanes to muons, subatomic particles, produced in Earth's atmosphere that live longer when moving at high speeds. Time dilation isn't just a theory, it's a physical reality. Now let's apply this to interstellar travel. Suppose a spacecraft were somehow able to reach 99.9% of the speed of light, an utterly extreme velocity, but useful for illustration. At that speed, the Lorentz factor, which quantifies how much time slows down, is about 22. This means that for every 22 years that pass on Earth, the travelers would experience just 1 year aboard their ship. In theory, they could make a trip to Proxima Centauri, 4.24 light-years away, in what would feel like just a few months of onboard time. But from Earth's perspective, the journey would still take over 4 years, assuming they could instantly accelerate and decelerate, which is impossible in practice. The gap grows even more dramatic at higher speeds. At 99.9999% of light speed, time for the travelers would slow by a factor of more than 700. A voyage that lasts mere months from their point of view could mean centuries passing back home. In other words, a crew could, in principle, travel across the galaxy and experience only a few years of subjective time, but by the time they returned, millions of years might have passed on Earth. This asymmetry is what makes time dilation both fascinating and tragic. It's not a form of time travel, it's time separation. For the crew, the journey would be swift and survivable, but for the civilization they left behind, it would be as though the travelers had vanished into history. Generations would rise and fall, languages would evolve, nations would crumble, and the descendants of those who watched the launch might not even remember the mission by the time any signal came back. The travelers might one day arrive at another star system, step out into a new world, and realize they are strangers in a universe that has moved on without them. And that's assuming the near impossible, that a ship could reach such speeds safely. The amount of energy required, as we discussed earlier, becomes astronomical even at 10% of light speed. Accelerating gradually over decades might ease the strain, but relativistic speeds still demand unfathomable amounts of fuel and protection. Moreover, at such velocities, every speck of dust in space becomes a potential bullet. Even a single grain of sand colliding with the spacecraft could release as much energy as a bomb, vaporizing entire sections of the hull.
Still, the concept of time dilation offers a haunting window into how motion and time are inseparably linked. In a universe governed by relativity, there is no universal clock ticking the same for everyone. Time itself bends and stretches depending on your velocity and the gravitational fields you move through.
Astronauts aboard the International Space Station, orbiting at 28,000 kilometers per hour, experience this effect on a tiny scale. Their clocks run slower than ours by a few microseconds per year. For them, time literally passes differently, though the difference is far too small to notice. Now scale that up to cosmic speeds. If one day we do build a ship capable of cruising near light speed, its crew would essentially skip forward in time relative to Earth. What feels like a few years to them could mean centuries or millennia outside. Humanity on Earth could evolve, vanish, or transform beyond recognition while they were still en route. The dream of relativistic travel thus hides a cruel irony. For the travelers, the trip might be bearable, but they would lose everything they ever knew in the process. This limitation shatters the romantic notion of interstellar empires or starfaring civilizations spanning galaxies in real time. Communication, coordination, and shared culture all depend on a synchronized sense of time, something relativity denies us once we move at relativistic speeds. You can't have a coherent interstellar civilization if each world experiences centuries while another experiences mere years. Time dilation turns the dream of galactic travel into a one-way leap into the future, severing all ties to the past. There's also the psychological weight of such a voyage. Imagine being part of a crew who knows they will never see home again. Not because they'll die before returning, but because the world they left behind will age thousands of years in their absence. Every message they send would take years or centuries to arrive, and any reply would come long after they were gone. In effect, the travelers would be exiled not just in space, but in time. So while time dilation offers a tantalizing way to make long journeys subjectively shorter, it doesn't solve the fundamental problem of communication and connection. For Earth, for mission control, and for the people waiting at home, the journey would still take exactly as long as the laws of physics demand. There is no cheat code to skip ahead, no way to beat light's relentless limit. The universe gives us one timeline, one speed, and one shared reality. And even when time itself bends to motion, causality stays intact. And that brings us to the next inescapable consequence of these enormous distances and cosmic limits: communication delays. Because even light, our fastest messenger, takes years to bridge the gulf between stars. Any conversation between Earth and a far-flung spacecraft would unfold at a glacial pace. Once you understand how time dilation separates travelers in experience, communication delay separates them in understanding. It's one more reminder that for now, our reach into the cosmos will always lag far behind our curiosity. When people imagine humanity exploring the far reaches of space, they often picture crisp radio chatter between mission control and brave astronauts, voices echoing across the void as if space were just another distant ocean to be crossed. But in reality, the cosmos does not allow for conversation at that scale. Even communication, the most fundamental link between explorers and the home they leave behind, begins to break down as distance increases. The reason is simple but unforgiving. Nothing can travel faster than light. And since our signals, whether radio waves, laser beams, or data transmissions, are light, the speed of light defines the absolute upper limit for how quickly information can move. Over cosmic distances, that speed is agonizingly slow. Even within our own solar system, communication delays are already significant. When NASA talks to the Mars rovers, the round-trip time for a message and response can be anywhere between 8 and 40 minutes, depending on where Earth and Mars are in their orbits. That means every command must be carefully planned, tested, and sent with no hope of immediate feedback. Engineers can't joystick a rover in real time. They must operate with patience and precision, waiting for each confirmation signal to crawl back through space. This delay is measured in minutes, yet it already transforms how we explore.
Now extend that concept outward. When NASA's New Horizons spacecraft made its historic flyby of Pluto in 2015, it was more than 4.8 billion kilometers away. At that distance, a signal traveling at light speed took about 4.5 hours just to reach Earth. That means by the time scientists received the first images of Pluto's surface, the spacecraft had already long passed the dwarf planet. Every instruction, every course correction, every data upload had to be planned and executed long before the moment of encounter. For all practical purposes, New Horizons was on its own. And Pluto is still within our solar system, a neighbor by galactic standards. When we move beyond that to Proxima Centauri, the nearest star, the challenge becomes nearly insurmountable. Proxima lies 4.24 light-years away, meaning that any signal, whether a radio transmission or a burst of laser light, would take 4.24 years to arrive. A simple "hello" sent from Earth today wouldn't reach any spacecraft there until late in the decade. And if that spacecraft replied immediately, we wouldn't receive the response for another 4.24 years after that. A single question and answer exchange would span nearly a decade. This isn't just an inconvenience, it changes the entire philosophy of spaceflight. There can be no real-time control, no immediate rescue, no interactive guidance. Any mission sent to another star must operate entirely autonomously, capable of making its own decisions, performing self-repairs, and handling emergencies without human oversight. In other words, the spacecraft must function more like a living organism, self-reliant, intelligent, and adaptive. Current technology is nowhere near that level of autonomy, though advancements in artificial intelligence may one day make it feasible. But even then, communication delays introduce deeper problems. Imagine a human crew traveling to another star. They could send updates home, but those updates would be ancient history by the time anyone received them. If they encountered danger, their cries for help would echo through space long after the situation had resolved, for better or worse. From Earth's perspective, they would effectively be ghosts from the past, speaking across a gulf of years. And for the crew, the messages coming from home would be memories from a world that no longer exists in real time. Loved ones could age, die, and be remembered by generations yet unborn before a single message exchange is completed. Even within a multi-ship mission traveling through deep space, communication would be sluggish if the vessels became separated by large distances. Coordinating maneuvers, sharing sensor data, or even maintaining formation could become impossible once delays stretch from minutes to hours or days. Every aspect of teamwork that we take for granted, collaboration, leadership, quick decision-making, dissolves when the very act of sending a message becomes a leap through time. This challenge extends beyond human missions. Consider a future in which we successfully place robotic probes around nearby stars. Those probes could collect incredible data, images of alien worlds, chemical signatures of strange atmospheres, perhaps even signs of life. But we would have to wait years to receive any of it. If we asked the probe to focus on a particular planet or repeat an observation, it would be another 8 to 10 years before we saw the results. In practice, these missions would operate more like time capsules, launched once, allowed to run independently, and studied long after the fact. Even communicating with our Voyager spacecraft, which are currently at the edge of the solar system, demonstrates the fragility of this connection. Each is about 24 billion kilometers away, and a signal from them takes more than 22 hours to reach Earth. The transmissions are faint, requiring vast radio antennas and NASA's Deep Space Network to detect the whispers of data trickling home. Eventually, those whispers will stop. Not because the spacecraft fail entirely, but because the signals will fade below our ability to hear them. In essence, they will fall silent not through destruction, but through distance. A haunting reminder that even light can be overwhelmed by the endless darkness. And when we think about communication delays in even a broader context, say a future where humans colonize multiple star systems, it becomes clear that our very notion of civilization would have to change. News, governance, science, and culture rely on rapid exchange of information. But if each colony is separated by years or decades of signal lag, then each will evolve independently. A united interstellar government or shared culture becomes a physical impossibility. Each world would be isolated, developing its own history and identity, like islands scattered across an ocean so vast that even the fastest ships take generations to cross it.
In that sense, communication delay is not just a technical barrier, it's a philosophical one. It forces us to confront what connection really means. If we can never speak to those who venture beyond the stars in real time, are they still part of our human story, or do they become something new, pioneers of a separate destiny, cut off by the sheer immensity of space-time? These vast delays remind us that the universe is not only enormous in distance, but slow in its response. Every light year is a wall of time. Every signal is a message sent into the past or the future, never truly the present. And as much as technology can improve our clarity or signal strength, Nothing can erase those years between question and answer. This isolation leads directly into the next great barrier of interstellar travel: the physical and engineering limitations of spacecraft themselves. Because even if we accepted the silence and the solitude, our ships, the fragile metal cocoons that carry us into the void, are nowhere near capable of surviving the stresses, radiation, and sheer duration of such journeys. The communication problem, then, is only part of a deeper truth. We are not just separated by distance, but by durability, by how long our creations and we ourselves can endure against the infinite. When we start to imagine journeys beyond our solar system, or even to its farthest edges, we inevitably confront a sobering reality. Our spacecraft are simply not built to last that long. The engineering challenges of deep space travel stretch far beyond propulsion or communication. They reach into the very fabric of what it means to build something that can survive for decades, centuries, or millennia in one of the harshest environments imaginable. Every part of a spacecraft, from its hull to its electronics, from its engines to its life support, faces obstacles that grow exponentially with distance and time. At first glance, a spacecraft might look sturdy and indestructible. It's covered in gleaming metal, its systems designed with precision, and its mission backed by decades of planning. But in truth, spacecraft are fragile machines, optimized for specific tasks and lifespans. Even the most durable probes we've ever built, like Voyager 1 and Voyager 2, were designed to operate for just a few years. Yet, thanks to extraordinary engineering, they've lasted nearly half a century. Still, their survival is a testament to over-engineering and luck, not a blueprint for interstellar endurance. The first challenge is material degradation. Space is not empty. It's filled with radiation, micrometeoroids, and temperature extremes that swing from blistering heat to bone-cracking cold. These forces eat away at spacecraft materials, slowly eroding, cracking, and weakening every surface. The constant bombardment of cosmic rays, high-energy particles traveling near light speed, can damage not only a ship's exterior, but also the delicate microchips and circuitry within. Over decades or centuries, this radiation would steadily fry onboard electronics, flip memory bits, and degrade insulation. Shielding can mitigate this, but shielding adds mass, and mass is the enemy of speed. Then there are micrometeoroids, tiny grains of dust drifting through interplanetary and interstellar space. At normal orbital speeds, a collision with one of these particles can pit a spacecraft's hull. But at relativistic speeds, even a grain the size of a sand particle becomes a deadly projectile. A collision at just 10% the speed of light could unleash the energy of a large bomb. Over decades, a spacecraft traveling through this cosmic shooting gallery would face countless impacts. The faster it moves, the more catastrophic each one becomes. Designing a shield thick enough to absorb such blows is theoretically possible, but it would be unimaginably heavy. Lighter options, such as electromagnetic deflectors or vapor clouds projected ahead of the ship, remain speculative and untested.
Thermal control is another enormous challenge. Spacecraft near the sun struggle to stay cool, while those traveling into the outer solar system must conserve every bit of heat to keep instruments from freezing. A mission to Pluto, for instance, must handle temperatures as low as -230 degrees Celsius. As a spacecraft moves beyond the warmth of sunlight, its onboard systems must generate and distribute heat internally, often using radioactive decay, like the radioisotope thermoelectric generators, or RTGs, used in Voyager, Cassini, and New Horizons. These power sources are remarkably reliable, but they decay over time. After a few decades, their output drops to a fraction of what it once was. For a multi-century or interstellar mission, even RTGs would eventually fail, leaving the spacecraft powerless and frozen. And if we add humans to the equation, the limitations become almost insurmountable. Life support systems are the most complex and delicate part of any crewed mission. They must provide air, water, food, and temperature regulation indefinitely, not for days or months, but potentially for generations. Recycling systems can recover a large portion of oxygen and water, but even on the International Space Station, which orbits just a few hundred kilometers above Earth, those systems require constant maintenance, spare parts, and human intervention. Over decades or centuries in deep space, parts would wear out, valves, bearings, pumps would fail. In space, there is no atmosphere to carry away heat or lubricate machinery naturally. Over time, lubricants evaporate or decompose, causing friction and damage. Engineers on Earth solve these problems through maintenance, but in deep space, replacement parts must come from within. This means a true interstellar spacecraft would need advanced manufacturing capabilities, 3D printers that can produce metal alloys, plastic seals, and electronic circuits from raw materials carried on board. That's far beyond what current 3D printing technology can do. Electronics face their own slow death. High-energy cosmic radiation doesn't just wear out circuits, it causes single-event upsets, random bit flips in memory or processing units that can crash systems or corrupt data. Space agencies already build radiation-hardened computers for missions like Juno or Voyager, but even those systems degrade over time. For interstellar missions lasting centuries, redundancy becomes essential. Multiple backup computers, self-correcting algorithms, and perhaps even artificial intelligence capable of rewriting its own code to adapt to failures. But with AI comes risk. Autonomy at that level means entrusting the entire mission and possibly human lives to a machine that must make its own decisions far beyond our supervision. And then there's the challenge of energy generation and storage. Solar panels become useless once a spacecraft moves too far from the sun. Batteries degrade chemically, losing capacity year by year. RTGs, as mentioned, decay slowly but surely. If we ever want a craft to operate for millennia, we'll need entirely new forms of power, perhaps small, self-contained fusion reactors or quantum batteries that can store energy with minimal loss. Until then, every mission we send outward has an expiration date built into its design. Taken together, these limitations paint a clear picture. Current spacecraft are temporary survivors, not eternal wanderers. They can cross planetary distances, but not interstellar ones. They are built to endure decades, not centuries. And the farther from Earth they go, the less control and repair we can offer them. Beyond a certain point, every spacecraft becomes a drifting relic, slowly succumbing to the cold logic of entropy. And yet, even in this sobering truth, there's a kind of beauty. Every mission we've launched, from Voyager to Pioneer, from Cassini to New Horizons, carries a message of endurance. These machines, tiny by cosmic standards, have survived radiation, cold, and time far longer than their designers imagined. Voyager 1 still speaks to us after nearly 50 years, sending faint signals from more than 24 billion kilometers away. Its systems are failing, but its journey continues, a silent testament to human persistence. Still, as we dream of traveling further, perhaps carrying humans beyond Pluto or even to another star, we must face not only the engineering limits of our machines, but the biological and psychological limits of ourselves. Because even if we built a spacecraft that could endure the ages, could we? Could a human being or even a generation survive the endless isolation, radiation, and loneliness of such a voyage? These questions take us to the next great barrier in the quest for the stars: human survival itself.
The question of human survival in deep space is perhaps the most honking and personal obstacle of all. Machines can be overbuilt,
Circuits can be hardened and fuels can be engineered, but the human body and mind are the result of millions of years of evolution in the gentle cradle of Earth. Our biology is tuned to one atmosphere of pressure, to a 24-hour day-night cycle, to the pull of gravity, the touch of air, the sound of other voices, and the simple rhythms of nature. When we step beyond our planet, we carry all of those ancient expectations with us. And the farther we go, the more those expectations become burdens we must fight to maintain. Inside a spacecraft, everything that sustains life must be artificially created and perfectly balanced. Air, water, food, and gravity, the fundamental conditions of survival, vanish the moment a spacecraft leaves Earth. Life support systems must continuously recycle oxygen and carbon dioxide, filter out toxins, purify water, and provide nutrition. Any small failure in this cycle can quickly become catastrophic. On the International Space Station, engineers are only hours away from sending replacement parts or emergency supplies, and astronauts can return to Earth within a day if something goes wrong. But on a voyage lasting decades or centuries, there are no supply ships, no repair crews, and no emergency exits. Even if all mechanical systems function perfectly, the human body itself begins to deteriorate in space. Without gravity, our muscles atrophy and our bones lose calcium, becoming brittle and weak. The cardiovascular system changes. The heart doesn't have to work as hard to pump blood, and over time, it begins to shrink. Vision can be impaired as fluids shift toward the head. The immune system weakens, wound healing slows, and radiation exposure accelerates cellular damage. Astronauts on the ISS exercise for hours every day to counteract these effects. But that's for missions lasting months, not lifetimes. Over decades in microgravity, the body might adapt in unpredictable ways, or it might simply fail. Radiation is the invisible killer that haunts every deep space mission. On Earth, we're protected by our planet's magnetic field and atmosphere, which deflect most cosmic rays and solar particles. In deep space, those defenses vanish. High-energy radiation constantly bombards the body, damaging DNA, increasing cancer risk, and potentially causing neurological harm. Even behind meters of shielding, prolonged exposure could be lethal. A journey to Mars, only a few years round trip, already exposes astronauts to radiation levels near or above safe lifetime limits. A voyage lasting centuries to another star would mean exposure beyond anything humans have ever endured. Unless we develop advanced radiation shielding, such as magnetic fields or water-based barriers, deep space travelers might not live long enough to see their destination. Then comes the challenge of time and isolation, the psychological weight of being cut off from everything familiar. Space is profoundly silent and unchanging. There are no seasons, no weather, no natural cycles to mark the passage of time. The stars outside the window do not twinkle. The same constellations hang frozen in place, and the horizon never rises or sets. For humans, who have evolved in a world of constant sensory and social input, such monotony can be deeply unsettling. Studies of astronauts, submarine crews, and Antarctic researchers showed that isolation and confinement can lead to depression, anxiety, insomnia, and cognitive decline. For a voyage lasting not months, but generations, these problems could become civilization-ending within the walls of a ship. A generation ship, one carrying humans who would live and die en route to a distant star, poses especially profound psychological and ethical challenges. The people born aboard such a vessel would have no memory of Earth, no sky, no concept of a horizon, no connection to the planet their ancestors came from. Their entire universe would be a metal shell hurtling through darkness. How would such a society maintain purpose? How would it handle conflict, power, or rebellion? Without careful cultural design, education, and mental health systems, a generation ship could easily descend into chaos or despair long before reaching its destination. Maintaining not just life, but meaning,
would be the hardest engineering task of all. Even for shorter, single-generation missions, loneliness becomes a formidable psychological barrier. Communication with Earth, as discussed earlier, would take years each way, too slow for real conversations. Crew members would know they might never see their families again, that by the time their messages arrive, loved ones may have aged or died. The emotional toll of such separation is hard to imagine. Astronauts on the ISS already struggle with feelings of isolation and disconnection after only months away, despite constant communication. Multiply that distance and time by millions, and the human spirit could falter under the crushing silence. Sleep and circadian rhythm disruption also present real dangers. Without natural sunlight and darkness, maintaining healthy sleep cycles becomes extremely difficult. Chronic sleep deprivation leads to irritability, poor judgment, and even hallucinations. On Earth, our bodies rely on subtle environmental cues, light intensity, temperature, sounds, to synchronize our internal clocks. In deep space, those cues disappear. Artificial lighting and routines can help, but over decades, small imbalances might accumulate, leading to mental and physical decline. Nutrition would also be a constant struggle. Food production in space currently depends on pre-packaged meals, but for long-term missions, that's impossible. Stored food loses nutrients over time, and bringing enough for centuries would be unfeasible. Future missions would require closed-loop agriculture, growing crops in recycled water and waste systems. Maintaining such a biosphere would be like balancing a miniature planet. One fungal infection, one chemical imbalance, or one crop failure could trigger starvation. Beyond the individual level, there's also the social dynamic of small, confined groups. Human history shows that even in comfortable, well-supplied environments, prolonged isolation can lead to conflict. Hierarchies form, resentments grow, and tiny disagreements can escalate when there's no escape. A deep space crew would need rigorous psychological screening, training, and perhaps even AI mediation to manage disputes. Yet no matter how well prepared they are, human nature can never be fully predicted. Over decades or generations, social evolution would take its own course, creating new cultures, beliefs, and possibly even dividing the crew into factions.
And then there's the fundamental issue of mortality. Even if life support is perfect and systems endure, humans are mortal beings. A voyage to another star could take centuries, meaning the original crew would die long before arrival. That raises profound questions. Would future generations willingly continue a journey they didn't choose? Would they honor the mission's purpose or abandon it? A spacecraft carrying thousands of humans could become a drifting microcosm of civilization, vulnerable to all its flaws and tragedies, magnified by isolation and time. Some have suggested solutions like cryogenic suspension or biological hibernation, freezing the body for centuries or slowing metabolism to a crawl. These ideas remain science fiction. Freezing living tissue without destroying it at the cellular level is far beyond current medical capability. Even if perfected, waking after centuries in deep space could bring disorientation, psychological trauma, or physical degeneration. Life extension through genetic engineering or nanomedicine might offer another path, but these are still theoretical and raise ethical questions of their own. Ultimately, human survival in deep space isn't just about biology or engineering. It's about identity. To travel for centuries through the void would mean redefining what it means to be human. We need to evolve, culturally, technologically, perhaps even genetically, to become a species capable of living independently of Earth. The bodies we have today, the minds shaped by blue skies and gravity, might simply not be suited for that future. And that realization leads naturally to a practical conclusion. Before humans can attempt such impossible journeys, robots must go first. Machines feel no isolation, need no food, and can operate indefinitely with the right power source. Unmanned probes are already our eyes and hands across the cosmos, paving the way where humans cannot yet follow. From Voyager to New Horizons, robotic explorers are the true pioneers of interstellar space,
and they may remain so for centuries to come. For now, as much as we dream about human explorers journeying beyond the boundaries of our solar system, the task of venturing into those distant frontiers belongs not to people, but to machines. Humanity's most courageous explorers are not made of flesh and blood. They are built of metal and circuits, traveling silently through the vacuum on missions that last decades, sometimes even beyond the lifespans of their creators. These robotic probes represent the only realistic and sustainable way we have to explore the vast distances that separate us from the outer planets, the Kuiper Belt, and the interstellar medium itself. Robotic missions solve nearly every insurmountable problem that human spaceflight faces. They don't require air, water, food, or sleep. They don't suffer from bone loss, depression, or radiation sickness. They can survive extreme temperatures, remain dormant for years, and awaken when needed. Their bodies can endure where human biology cannot, in the vacuum beyond sunlight, in the cold shadow of distant worlds, or drifting through cosmic radiation fields that would kill a human in hours. Robots are, in many ways, the perfect ambassadors for a universe that is fundamentally hostile to life as we know it. Consider the Voyager spacecraft, launched in 1977. These two robotic explorers were designed for a mission of just 5 years, to study Jupiter and Saturn, but they went far beyond anyone's expectations. Decades later, Voyager 1 and Voyager 2 are still transmitting faint whispers of data from beyond the edge of the solar system. Voyager 1 is now more than 24 billion kilometers from Earth, having entered interstellar space in 2012. Its instruments continue to measure the density and magnetic fields of the interstellar medium, the thin gas and plasma between the stars. Although its radioisotope power supply is fading and some instruments have been shut down, it remains humanity's most distant object, a silent traveler still carrying a message from Earth in the form of the Golden Record, a phonograph disc containing sounds and images of our world. Voyager probes prove what robotic missions can achieve with careful engineering and foresight. Despite being built with 1970s technology, computers far less powerful than a modern watch, they continue to function after nearly half a century in deep space. This endurance is a testament to the simplicity and resilience of robotic exploration. There are no human needs to sustain, no fragile psychology to manage, only the slow, steady ticking of automated systems doing their work across the gulf of time. Following Voyager's legacy came New Horizons, launched in 2006. Its mission to explore the Pluto system and the Kuiper Belt beyond. After traveling for 9.5 years and covering over 5 billion kilometers, New Horizons reached Pluto in July 2015, the first spacecraft ever to visit the distant dwarf planet. The images it sent back were breathtaking. Icy plains of nitrogen, towering mountains of water ice, and a thin blue atmosphere illuminated by the distant sun. The world that had once appeared as the blurry smudge in telescopes became a detailed, living landscape. And all of it was made possible by a robot no larger than a grand piano, guided by a team of scientists billions of kilometers away. After completing its Pluto flyby, New Horizons continued its journey deeper into the Kuiper Belt, encountering another distant object, Arrokoth, in 2019. Each transmission from the spacecraft took over 6 hours to reach Earth, yet the data it returned expanded our understanding of the early solar system and the building blocks of planets. These missions demonstrate how robotic probes act as our extensions into places we may never physically go, each one a set of electronic eyes and instruments gathering knowledge on our behalf.
Even now, multiple robotic explorers are at work throughout the solar system. NASA's Juno orbits Jupiter, studying its storms, gravity, and magnetic field. The Parker Solar Probe dives closer to the Sun than any spacecraft before it, enduring temperatures that would melt metal. OSIRIS-REx traveled to an asteroid, collected samples, and returned them to Earth, a feat that combines precision engineering and interplanetary choreography. The James Webb Space Telescope, positioned nearly 1.5 million kilometers away, peers into the earliest epochs of the universe, seeing galaxies as they were billions of years ago. Each of these robotic missions is part of a grand, interconnected story, the gradual unfolding of humanity's reach into the cosmos. Unlike human explorers, these machines don't carry emotion, but they carry intention.
They are the physical embodiment of human curiosity, intellect, and imagination, built to go where our bodies cannot and to survive what we cannot endure. Their success shows that while we may be far from interstellar travel, we already possess the ability to explore and learn from the farthest reaches of our solar neighborhood. But even robotic probes face their own limits. The farther they go, the weaker their signals become. The Voyager spacecraft, for instance, transmit with only about 20 watts of power, roughly the energy of a refrigerator light bulb. Yet their signals, when they reach Earth, are so faint that NASA's massive radio antennas must detect energy levels a billion times weaker than a cell phone signal. Beyond a certain distance, even these signals fade into the cosmic background noise. Without an enormous leap in communication technology, such as laser-based transmission or quantum communication, there's a point where a spacecraft's voice simply becomes too quiet to hear. Despite this, the future of robotic exploration holds extraordinary promise. Projects like Breakthrough Starshot envision sending swarms of microprobes to nearby stars, propelled by powerful ground-based lasers that push them on light sails. These spacecraft would be no larger than a postage stamp, yet could reach 20% of the speed of light, allowing them to reach Proxima Centauri in just over 20 years. The technology to make this real doesn't yet exist, but the idea marks a turning point, a recognition that for interstellar travel, miniaturization and autonomy are key. We may never send giant starships full of people, but we could send fleets of intelligent probes, each carrying sensors, cameras, and digital minds capable of discovery. In essence, robot explorers are the bridge between imagination and reality, between the dreams of science fiction and the hard truth of physics. They show us that exploration doesn't require our physical presence, only our ingenuity and will to know. Every signal they send back across the void is a whisper of triumph against the silence of space. Still, while robotic exploration has proven itself again and again, it also reminds us of the scale of what lies beyond. The leap from visiting Pluto to reaching Proxima Centauri is not a matter of better machines alone. It's a jump across a chasm that dwarfs our current capabilities. To understand just how immense that leap really is, we need to compare the scope and scale of these missions. The difference between sending a spacecraft to Pluto and attempting a journey to Proxima Centauri. When we compare the scale of missions, the difference between sending a spacecraft to Pluto and attempting a journey to Proxima Centauri, we are essentially comparing the difference between crossing a city and crossing an ocean the size of the universe. Both sound like going somewhere far, but in terms of energy, time, and scale, they belong to entirely different categories of possibility. Reaching Pluto, while daunting and impressive, is a feat of interplanetary travel. Still within the gravitational grasp of our Sun, still governed by orbits, and still connected to Earth through the faint but steady reach of radio waves. But reaching Proxima Centauri, the nearest star beyond our solar system, crosses the boundary from interplanetary to interstellar travel, a leap so vast that the challenges multiply exponentially, pushing far beyond the realm of current technology and even into the limits of fundamental physics.
Let's start by grounding ourselves in the numbers. Pluto, on average, sits about 5.9 billion kilometers from Earth, or roughly 39 astronomical units from the Sun. That's unimaginably far by human standards, more than 30 times the distance from Earth to Jupiter. Yet, New Horizons made the journey in under a decade, traveling at about 58,000 kilometers per hour, and it's still within the Sun's gravitational domain. We could, with existing propulsion technology, plan similar missions again, faster, perhaps more efficient, but not fundamentally impossible. The spacecraft remains powered, guided by sunlight or radioisotope decay, and within reach of our communication networks. Every photon of sunlight it receives, every particle of solar wind it encounters, still ties it back to the warmth of our solar home. Now stretch that scale outward to Proxima Centauri, our closest neighboring star, about 4.24 light-years away.
That's approximately 40 trillion kilometers, or more than 268,000 astronomical units. To put it another way, if the solar system were the size of a dinner plate, Proxima Centauri would be another plate sitting thousands of kilometers away. The difference in distance between Pluto and Proxima Centauri is not a matter of a few times farther. It's a factor of nearly 7 million. The energy and time required to cover that gap increase not linearly, but almost incomprehensibly. To reach Pluto, you need to overcome the pull of the Sun's gravity and cruise through the outer planets. To reach Proxima Centauri, you need to escape the Sun's entire gravitational influence and then cross a void so vast that no sunlight reaches it meaningfully. Beyond the heliosphere, the bubble of particles and magnetic field that surrounds our solar system, lies the interstellar medium, a sparse ocean of hydrogen, dust, and radiation stretching endlessly between the stars. A spacecraft entering that realm is no longer tethered to the solar system. It becomes a wanderer in the galaxy. The difference in communication time alone underscores the scale. When New Horizons sent data from Pluto, the signals took 4.5 hours to reach Earth. That delay was manageable, a challenge but not a deal-breaker. But if we had a spacecraft orbiting Proxima Centauri today, its messages would take 4.24 years to reach us, one way. A simple hello and received would take nearly a decade. There can be no real-time commands, no adjustments, no monitoring in any human sense. Every decision that probe makes must be autonomous, designed decades before it ever arrives. Then there's travel time. New Horizons reached Pluto in 9.5 years. At the same speed, about 16 kilometers per second, a spacecraft heading to Proxima Centauri would take over 75,000 years to get there. To put that into perspective, 75,000 years ago, Homo sapiens were sharing the planet with Neanderthals and painting on cave walls. Our entire recorded human history would fit several times over within the travel time of a single such journey. Even the fastest human-made object, the Parker Solar Probe, which will reach speeds of around 700,000 kilometers per hour, would still take nearly 7,000 years to cover that same distance. And it's not just about time, it's about sustainability. A probe to Pluto needs enough power to last decades. New Horizons uses a small nuclear generator that will continue providing power for perhaps 20 to 30 years total. A probe to Proxima Centauri would need an energy source that lasts millennia, functioning without maintenance, through collisions with micrometeoroids, through radiation bombardment, and through the cold vacuum of deep space. Current power systems, whether solar or nuclear, simply don't last that long. No known material or circuit can reliably endure tens of thousands of years of cosmic exposure without degradation. Even if we solve the propulsion problem, say with futuristic technologies like light sails or nuclear fusion drives, the engineering scale of an interstellar mission dwarfs anything we've ever attempted. A trip to Pluto requires hitting a moving target within a solar system we understand with exquisite precision. A trip to another star requires navigating across interstellar space where gravitational influences shift subtly, radiation levels vary, and hazards like interstellar dust can destroy a craft traveling at even a small fraction of light speed. At such velocities, even a particle the size of a grain of sand could release enough energy on impact to cripple or vaporize a spacecraft. Shielding against that would require mass, and mass slows acceleration, a constant, brutal trade-off that defines all space engineering. Another difference lies in the scientific purpose and payoff. A mission to Pluto yields decades of data within a human lifetime. Scientists who design and launch the probe live to see its results, analyze its findings, and build on them. A mission to Proxima Centauri, at least with present-day speeds, would not return data for tens of thousands of generations. By the time its signals reached Earth, human civilization, if it still existed, might be entirely unrecognizable. Nations, languages, and technologies would have changed countless times. From a practical standpoint, an interstellar mission is not just a scientific challenge, it's a philosophical one. Who'd we build it for if we will never see the results? Even when we imagine future possibilities like Breakthrough Starshot, which proposes microprobes traveling at 20% of light speed to reach Proxima Centauri in about 20 years, the engineering challenge is staggering. These probes would experience immense acceleration forces, thousands of times Earth's gravity, and would have to survive without deceleration on arrival, meaning they'd flash past the star system in seconds. Gathering meaningful data in that instant would require sensors, cameras, and communication systems far beyond anything we have today. And transmitting that data back across 4 light-years would require a power source so efficient that it borders on the edge of physical possibility.
In short, traveling to Pluto and traveling to Proxima Centauri are separated not just by distance, but by order of reality. One is a feat of perseverance within our solar backyard. The other is a challenge that touches the boundaries of time, physics, and human imagination. When New Horizons reached Pluto, it was like sending a message across a vast desert and getting a reply within a lifetime. Reaching Proxima Centauri would be like throwing a bottle into an infinite ocean with no certainty that anyone or anything would ever receive it. And yet, the comparison is not meant to discourage us. It is meant to illuminate the magnitude of the challenge, to show that while Pluto was the edge of one map, Proxima Centauri is the beginning of another entirely. The difference reminds us that, in cosmic terms, we are still learning to walk before we can run, still learning to navigate our own solar system before we can dream of leaping to the stars. But if distance and time are immense barriers, the universe poses even more dangers along the way. Beyond the solar wind and planetary orbits lies a wilderness filled with hazards, invisible, deadly forces that would threaten any spacecraft daring to venture between the stars. To understand why interstellar travel remains nearly impossible, we must explore these threats, the cosmic hazards that guard the space between suns. Space is not empty. It may look like an endless black void, but it's far from a tranquil or harmless expanse. Between stars, planets, and galaxies lies a harsh, invisible battleground of radiation, dust, magnetic fields, and charged particles, a deadly sea that no spacecraft can yet fully withstand. When we talk about the impossibility of traveling to places like Proxima Centauri, the vast distances are only part of the story. Even if we somehow solve the problem of propulsion, navigation, and time, the universe itself presents us with an environment so extreme that simply surviving the trip becomes an almost insurmountable challenge. The first and most pervasive danger is radiation, a constant, invisible bombardment of high-energy particles from all directions. Within our solar system, the sun is the main source of radiation. Its solar flares and coronal mass ejections hurl charged particles across space, and our spacecraft, as well as astronauts aboard the ISS, are protected to some degree by Earth's magnetic field and atmosphere. But once you venture beyond that shield, you enter a realm dominated by galactic cosmic rays, or GCRs. These are not just simple rays of light or X-rays, they are subatomic particles, mostly protons and atomic nuclei, traveling at nearly the speed of light, originating from supernovae and other high-energy cosmic events. Each cosmic ray that strikes a spacecraft can pass straight through metal, damaging electronics and altering atomic structures. Over time, this causes materials to become brittle, circuits to degrade, and systems to fail. For human travelers, exposure to these rays would be lethal. For robots, the problem is one of longevity. Electronic components can be shielded, but over tens of thousands of years, even the BIS shielding will erode, allowing radiation to slowly but relentlessly destroy the crash systems. Now consider a spacecraft moving at even a fraction of the speed of light, say 10% or 20%. At such velocities, the impact energy of every particle in space becomes devastating. A single hydrogen atom, the most common element in the interstellar medium, would strike the craft with enormous kinetic energy,
enough to cause molecular-level damage. The faster you travel, the more those individual particles begin to act like bullets of radiation, bombarding the front of the spacecraft with unstoppable fury. The spacecraft would effectively be flying into a continuous atomic storm, each collision generating heat and radiation that could melt or vaporize its forward surfaces. To protect against this, engineers have theorized Whipple shields, layers of material designed to absorb and disperse impacts. These work well for micrometeoroid protection in Earth orbit or interplanetary space, but at relativistic speeds, even dust grains become catastrophic. A single grain of interstellar dust, smaller than a pinhead, could strike with the force of an artillery shell. The kinetic energy released would be equivalent to several kilograms of TNT, enough to puncture or annihilate a spacecraft traveling at high velocity. Over the course of an interstellar voyage, encountering billions of such particles would guarantee eventual destruction unless unprecedented protection methods were developed. And that brings us to another deadly component of space: micrometeoroids and the interstellar medium. Contrary to the word vacuum, space is not completely empty. The interstellar medium, the space between stars, contains gas, dust, plasma, and cosmic debris. On average, there are only a few atoms per cubic centimeter, but across light years of travel, those few atoms add up. When traveling through interstellar space, a spacecraft's path is more like sailing through a thin fog of high-energy particles, not gliding through emptiness. In our solar system, micrometeoroids are already a significant threat. The International Space Station and satellites are constantly pelted by microscopic fragments of rock and metal, traveling at speeds up to 70,000 kilometers per hour. Even particles smaller than a grain of sand can punch tiny craters in metal surfaces or shatter windows. Now imagine scaling that up to interstellar travel, where the relative speed might be hundreds or thousands of times greater. Every impact becomes a potential catastrophe.
The interstellar medium also presents an erosion hazard. Over time, the constant bombardment of particles would slowly strip away a spacecraft's surface, molecule by molecule. Its exterior could pit, deform, and weaken until the structural integrity fails. Radiation-induced chemical reactions could alter the material's properties, making metals brittle or causing polymers to disintegrate. For a journey lasting thousands of years, even these tiny, cumulative effects could spell disaster long before the spacecraft reaches its destination. Then there's the threat of electromagnetic interference. The interstellar environment is filled with fluctuating magnetic fields and cosmic electromagnetic radiation. These can induce electric currents in the spacecraft's systems, disrupting communications or damaging sensitive electronics. Cosmic ray strikes can also cause bit flips, single particle events that alter data in a computer's memory. For long-duration autonomous missions, where self-correction and reliability are critical, even small glitches could have devastating consequences. Without human intervention, a single uncorrected software error could render a probe inoperative forever. Temperature extremes add yet another layer of peril. Spacecraft traveling away from the sun must endure the near absolute zero cold of interstellar space. The absence of sunlight means almost no natural warmth. Components must rely on internal heat generation or radioisotope decay to prevent freezing. At the same time, any side exposed to a nearby star or heated by particle collisions might experience intense thermal stress. Materials expand and contract differently under these conditions, potentially causing structural cracks, seal failures, or distortions. Maintaining thermal stability across millennia is a feat no known engineering material can achieve. And even if a spacecraft somehow survived all this, radiation, particle impacts, magnetic storms, and temperature extremes, there's the problem of detection and navigation. The interstellar medium is opaque to some wavelengths of light, meaning sensors may be unable to clearly detect nearby hazards or even the target star system. Navigational accuracy must be maintained to fractions of a degree over light years, without external guidance.
Tiny errors in trajectory could cause a probe to miss its destination by millions of kilometers. Course corrections would require propulsion and fuel, both of which are scarce in deep space. These hazards together form a nearly impenetrable gauntlet between the stars. Each problem alone might seem solvable with advanced materials or clever design, but in combination, they make interstellar travel a monumental challenge, not merely an engineering problem, but one that tests the limits of physics, chemistry, and time itself. To endure them, future spacecraft would need revolutionary advancements in every area: self-healing materials, magnetic deflector shields, autonomous AI navigation, and perhaps even energy fields capable of repelling radiation and dust. These ideas sound like science fiction because for now, they are. Yet they represent the kind of radical innovation required if humanity ever hopes to build a machine capable of surviving the deep space wilderness. These cosmic hazards don't just block our path physically. They remind us of how violent and dynamic the universe truly is. Space is not the serene black canvas it appears to be. It's a realm of constant motion, impact, and radiation. To cross it safely would mean creating a vessel that is not just fast, but nearly indestructible, self-sustaining, and intelligent enough to care for itself in total isolation for centuries. And so, while we marvel at the achievements of Voyager and New Horizons, we must recognize that they are only skimming the calm edges of an ocean whose depths we can barely imagine. Beyond those edges lies a storm of physics waiting to tear apart anything fragile or unprepared. But even in the face of such overwhelming danger, the human spirit persists in seeking solutions. And that brings us to the next stage in our exploration: the propulsion innovations. The bold, theoretical ideas like nuclear engines, antimatter drives, and light sails that might one day make it possible to cross those lethal distances safely and swiftly. If the interstellar environment presents an unyielding expanse of space and danger, then propulsion, the art of moving through that void, is humanity's ultimate test of imagination and engineering. Every journey into the stars begins with a question: how do we go faster? Our current rockets, whether powered by chemical combustion or ion engines, are extraordinary in their precision and reliability, but pitifully slow when measured against the scale of interstellar travel. To cross the solar system, they are adequate. To cross to another star, they are almost meaningless. And so scientists and dreamers alike have spent decades devising revolutionary propulsion concepts. Ideas that, in theory, could cut a journey of tens of thousands of years down to centuries or even decades. Among these, the most famous and most plausible in the near term is nuclear propulsion. Instead of burning chemical fuels like hydrogen and oxygen, a nuclear rocket would use the immense energy released by splitting or fusing atoms. The simplest version, called nuclear thermal propulsion, heats hydrogen using a nuclear reactor and expels it through a nozzle, producing thrust far more efficiently than chemical rockets. This concept isn't science fiction. It was actually tested on Earth during the 1960s under NASA's NERVA program. The results were promising. Nuclear rockets could potentially double or triple the efficiency of conventional engines, cutting travel time to Mars in half. However, while nuclear propulsion offers significant improvements for interplanetary travel, it remains far from the speeds required for interstellar missions. Even at its theoretical best, an NTP engine could achieve a few dozen kilometers per second. Impressive, but not transformative. To reach another star within a human lifetime, we would need nuclear fusion propulsion, a far more powerful and difficult technology that harnesses the same reaction powering the sun. In fusion, light atomic nuclei, like hydrogen isotopes, combine under immense heat and pressure to release vast amounts of energy. A fusion-powered spacecraft, if realized, could in theory reach a few % of the speed of light, enough to make interstellar travel conceivable, if still immensely challenging.
The most famous design based on this principle is the Daedalus project, proposed in the 1970s by the British Interplanetary Society. Daedalus envisioned a colossal, two-stage spacecraft powered by pulsed fusion reactions using helium-3 and deuterium fuel pellets. It would accelerate for 4 years, coast for decades, and reach 12% of light speed, arriving at the nearby star Barnard Star in about 50 years. It was a beautiful design, both in its ambition and its realism. But the engineering requirements were staggering. Tens of thousands of tons of fuel, massive magnetic containment systems, and technology that remains far beyond our current reach. We cannot yet produce controlled fusion for power on Earth, let alone use it to propel a spacecraft through space. Still, fusion propulsion remains one of humanity's most credible long-term hopes. Projects like Project Icarus and recent private fusion startups continue to explore ways to make it feasible. The idea persists because fusion offers something critical, a high energy-to-mass ratio, meaning it could, theoretically, provide sustained thrust without requiring impossible amounts of fuel. Yet every step toward this goal is hindered by one word: control. Achieving stable fusion reactions, containing them safely, and turning that energy into directed propulsion is one of the hardest problems in all of physics. Beyond fusion lies the even more exotic possibility of antimatter propulsion, the ultimate energy source known to physics. When matter and antimatter collide, they annihilate each other completely, releasing 100% of their mass as energy, according to Einstein's famous equation, E equals mc squared. 1 gram of matter reacting with 1 gram of antimatter would produce an explosion equivalent to nearly 40 kilotons of TNT, roughly twice the power of the Hiroshima bomb. Harnessing that energy for propulsion could, in theory, accelerate a spacecraft to significant fractions of the speed of light. Antimatter engines come in 2 main flavors: antimatter rockets, which use the annihilation reaction to heat propellant, and beam core drives, which directly channel the annihilation particles out the back for thrust. The latter could, theoretically, achieve efficiencies near the physical limit. But there's a catch. Actually, several monumental catches. First, antimatter doesn't exist naturally in large amounts. It must be manufactured in particle accelerators, and at present rates, producing just 1 gram would cost trillions of dollars and take millions of years to produce. Second, storing antimatter safely is nearly impossible. It annihilates instantly on contact with ordinary matter, meaning it must be kept suspended in perfect magnetic traps, technology that currently only works for tiny fractions of a second and for subatomic quantities. One containment failure, one power glitch, and the spacecraft, along with everything aboard it, would be vaporized. Even if we solve those problems, there's the issue of efficiency and waste heat. Converting the annihilation energy into directed thrust without melting the engine or vaporizing the ship is another colossal challenge. The heat management systems alone would add prohibitive mass, further complicating design. For all its elegance in theory, antimatter propulsion today remains as distant as warp drive, tantalizing but impractical. Speaking of elegance, one of the most poetic and visionary propulsion concepts is the light sail, or solar sail. Instead of burning fuel, a light sail uses the pressure of photons, the particles of light, to push a spacecraft forward. Every photon carries a tiny bit of momentum, and when it reflects off a mirrored surface, it imparts a minuscule push. In the vacuum of space, where there's no friction, those tiny pushes accumulate over time. A light sail powered by sunlight could, over months and years, reach enormous speeds, tens of thousands of kilometers per hour, without expending any fuel. Light sails are not just theoretical. Japan's Ikaro's mission in 2010 successfully demonstrated solar sail technology, and private efforts like the Planetary Society's Light Sail 2 have proven it further. But sunlight alone can only push so far. To reach interstellar speeds, we would need something more intense, like laser-driven sails, where massive ground-based or orbital lasers bombard a reflective sail, accelerating it to a fraction of the speed of light.
This is the principle behind the Breakthrough Starshot project, which envisions sending tiny gram-scale probes to Proxima Centauri within 20 years. The concept is breathtaking, but the engineering challenges remain enormous. The sail must survive acceleration forces thousands of times stronger than gravity without tearing. It must reflect the laser perfectly to avoid vaporizing itself. The laser array itself would need to deliver gigawatts of power and maintain focus over millions of kilometers. And once the probe reached its destination, it would have no way to slow down. It would simply zip through the target system in seconds. Moreover, transmitting data back across 4 light-years with only milliwatts of onboard power seems almost impossible.
Beyond these more grounded ideas lie even wilder dreams: warp drives, wormholes, and quantum propulsion. Theoretical models like the Alcubierre drive propose bending space-time itself, contracting it in front of a ship and expanding it behind to move faster than light without violating relativity. While mathematically intriguing, such concepts require negative energy or exotic matter, which may not even exist. The energy required to warp space enough to move a small spacecraft would exceed the total energy output of entire stars. In other words, they remain purely speculative, beautiful thought experiments that inspire science fiction more than engineering. The common thread in all these propulsion innovations is that they are not fundamentally impossible. They are impractical with our current technology. Each one bumps against limits of materials, energy production, and physics that humanity is only beginning to approach. They show us what might be possible centuries from now, but they also reveal how far we still have to go. Every new propulsion idea, from nuclear fusion to antimatter, brings us closer to the stars conceptually, but each also underscores the enormous energy barrier we must overcome. The universe gives us no shortcuts. To go faster, we must pay the price in energy, precision, and risk. Until we can master those costs, our dreams of interstellar travel will remain confined to simulations, laboratories, and imagination. Still, that imagination is not wasted. Every discussion of propulsion, every concept paper, experiment, or test moves us closer to understanding what's truly possible. And even if we never build a starship, the pursuit itself pushes science forward, driving advancements in energy, materials, and artificial intelligence that ripple back into life on Earth. But propulsion is only part of the story. Even if we found a way to travel fast and survive the journey, there remains an obstacle that no engine can overcome: time itself. The universe moves at its own pace, and human civilization may change beyond recognition long before a starship ever arrives at its destination. The next great question, then, isn't just technological, it's temporal. What does it mean to start a journey that might outlast the civilization that began it? Time, more than distance, danger, or even energy, is perhaps the most profound barrier standing between humanity and the stars. We often think of time as something linear and predictable, measured in seconds, minutes, and years. But when you begin to contemplate a voyage that would take thousands or even tens of thousands of years, time stops being a simple measurement. It becomes a force as vast and uncontrollable as gravity itself. Even if technology were to advance to the point where interstellar travel became physically possible, time would still impose a limit that transcends engineering. The scale of the universe doesn't just stretch across space, it stretches across epochs, challenging the very continuity of human civilization. Consider this: the fastest spacecraft humanity has ever built, the Parker Solar Probe, travels at roughly 700,000 kilometers per hour. That's an incredible speed, capable of circling Earth nearly 20 times in a single day. Yet, even at that velocity, it would take over 6,600 years just to reach Pluto's orbit again, and nearly 6,600 centuries to reach Proxima Centauri. Those numbers don't just represent distance, they represent time itself as a barrier. Thousands of years ago, humanity was still in the Bronze Age. We hadn't invented writing in many parts of the world. Civilizations rose and fell, languages were born and forgotten, and entire empires came and went.
all within time spans shorter than the journey it would take for even our fastest probes to reach the next star. When you look at it this way, it becomes clear. Even if we launched a mission to Proxima Centauri tomorrow, the people who built it, and even their descendants for hundreds of generations, would be long gone before it arrived. Humanity itself might evolve, collapse, or transform into something unrecognizable before that craft ever transmitted a single signal back home. Civilizations are dynamic. They rise, fall, rebuild, and reinvent themselves. Expecting any culture to maintain a single mission, unbroken, for tens of millennia is almost inconceivable. This introduces what scientists and philosophers sometimes call the problem of temporal continuity. Technology might advance faster than the mission can progress. Imagine we launch a ship today that will reach another star in 50,000 years. Within just 500 years, or even 50, it's entirely possible that humanity would invent a new propulsion system capable of making the same journey in only a few decades. Suddenly, the original mission becomes obsolete before it's even halfway there. The first starship could be overtaken by a faster one launched centuries later, rendering the original effort a historical curiosity drifting through the void.
This paradox is sometimes referred to as the waiting problem of interstellar travel. Why send a ship today if a better one can be built tomorrow? If you wait for technology to improve, you can always send a faster mission that will arrive sooner. But if you wait forever, you'll never go at all. The universe doesn't stand still, and neither does progress. Every generation that looks to the stars must balance ambition with patience, recognizing that time doesn't only erode distance, it erodes relevance. There's also the question of societal longevity. Maintaining a mission across centuries or millennia isn't just a technical problem, it's a cultural one. Who maintains the records? Who pays the cost? Who ensures that hundreds or thousands of years in the future, someone still remembers why a distant probe was sent in the first place? Even our longest-running missions, like Voyager 1 and Voyager 2, are mere infants in the cosmic timeline. They've been traveling for nearly half a century, and yet even now their fading signals and weakening power supplies remind us that nothing built by human hands lasts forever. For a true interstellar mission, we'd have to think in generational terms. The idea of a generation ship, a massive spacecraft carrying thousands of people who live and die over centuries as their descendants continue the voyage, has long been a staple of science fiction. But even in theory, the challenges are staggering. How do you maintain a stable, functioning society isolated in a sealed metal world for 1,000 years? How do you prevent cultural stagnation, social decay, or rebellion? Would the great-great-grandchildren of the original crew even care about the mission's goal, or would they see themselves as inhabitants of their own self-contained world with no connection to the planet their ancestors left behind? Even our longest-running missions, like Voyager 1 and Voyager 2, are mere infants in the cosmic timeline. They've been traveling for nearly half a century, and yet even now, their fading signals and weakening power supplies remind us that nothing built by human hands lasts forever. For a true interstellar mission, we'd have to think in generational terms. The idea of a generation ship, a massive spacecraft carrying thousands of people who live and die over centuries as their descendants continue the voyage, has long been a staple of science fiction. But even in theory, the challenges are staggering. How do you maintain a stable, functioning society isolated in a sealed metal world for 1,000 years? How do you prevent cultural stagnation, social decay, or rebellion? Would the great-great-grandchildren of the original crew even care about the mission's goal, or would they see themselves as inhabitants of their own self-contained world with no connection to the planet their ancestors left behind? Even our longest-running missions, like Voyager 1 and Voyager 2, are mere infants in the cosmic timeline. They've been traveling for nearly half a century, and yet, even now, their fading signals and weakening power supplies remind us that nothing built by human hands lasts forever. For a true interstellar mission, we'd have to think in generational terms. The idea of a generation ship or long voyage spacecraft requires a ship to be capable of self-sustaining support, which thrives on AI,
Essentially, it would have to evolve as it travels, a living machine, not just a vessel. That level of autonomy borders on artificial sentience, something we have not yet achieved and may not for centuries. But even if technology one day allows such self-sustaining ships, the question of time still lingers on a deeper philosophical level. What happens if humanity changes so drastically that by the time a starship arrives, the civilization that launched it no longer exists in any recognizable form? Perhaps humans will merge with AI, upload consciousness into digital form, or colonize a solar system so completely that the idea of a mission to another star becomes irrelevant. The message from that long-traveling ship might reach a future where no one even speaks our languages or remembers our struggles. A whisper from an extinct past arriving in a universe that has moved on. This perspective reveals the fragility of continuity, the challenge of linking intent across millennia. When we send a spacecraft to another world, we're not just sending metal and circuits, we're sending meaning. A story about who we are and what we value. But stories can fade. What if the message we send out to the cosmos reaches not descendants, but strangers? Or worse, no one at all? The irony is profound. As we strive to conquer the problem of space, we are confronted with the problem of time, and in doing so, we must confront our own impermanence. Civilizations change, knowledge shifts, and priorities evolve. The humanity of today is not the humanity of tomorrow. If we ever attempt to build an interstellar civilization, it will not only require technological innovation, but a redefinition of endurance, a cultural and moral commitment to the future that surpasses any that has ever existed. To embark on a voyage to another star is not just to cross the cosmos, it's to plant a seed that may not bloom until long after the gardeners are gone. That requires a faith, not in physics, but in the continuity of purpose. Until we can ensure that continuity, the problem of time will remain as formidable as the problem of distance. And yet, even in the face of this near-eternal barrier, humanity continues to dream. Because to dream of the stars is, in a sense, to defy time itself, to insist that something of us will endure. Whether we reach those distant suns or not, our yearning to try marks us as a species that refuses to be confined to the present. Still, as we ponder this timeless struggle, another question emerges. A question not of physics or endurance, but of meaning. If it may take eons to reach the stars, and our descendants will be unrecognizable when we do, what does impossible really mean? Is it truly impossible, or just beyond the horizon of our current age? That reflection leads us into the next great idea, the philosophical angle, where we examine the very nature of impossibility and what it means to reach beyond our grasp. When we talk about the impossible, what do we actually mean? The word carries weight. It sounds final, absolute, and unyielding. Yet history has shown again and again that what once seemed impossible often turns out merely to be a reflection of our current limitations, not a law of nature. To call something impossible is in many ways to draw a line around the horizon of human understanding, a line that shifts each time we push a little further into the unknown. The philosophical challenge of space exploration, particularly journeys to places like Pluto or Proxima Centauri, lies in understanding that distinction. What is truly impossible and what is simply not yet possible?
For centuries, humanity has stood at the edge of the unknown and declared, "This cannot be done." Crossing the oceans, flying through the skies, splitting the atom, landing on the moon, all of these were once dismissed as impossibilities. Each time, the barrier was not the universe itself, but our own imagination. When Galileo turned his telescope toward the heavens, he shattered the illusion that the cosmos was perfect and unchanging. When the Wright brothers launched their fragile machine into the air, they defied every law of common sense known to engineers of their day. When Apollo 11 touched down on the lunar surface, humanity proved that impossible could be rewritten in real time. Yet space, especially interstellar space, is of an entirely different order. The scales are vast beyond comprehension. The obstacles are not just technical, but existential. So we must ask, does impossible here mean that it can never be done, or simply that it cannot be done by us, now, or perhaps even by humans at all? From a scientific perspective, certain things truly are impossible.
The speed of light, for instance, is not just a technical limit, it is a fundamental boundary written into the fabric of the universe. According to Einstein's theory of relativity, as an object with mass approaches the speed of light, its energy requirement grows toward infinity. No amount of ingenuity or technology can change that. It is not a failure of engineering, but a law of nature. In that sense, traveling faster than light may indeed be impossible in the strictest physical sense, unless some future theory of physics rewrites our understanding of space-time itself. But here's where the philosophical nuance comes in. The universe's laws may be fixed, but our relationship to them is not. What seems impossible within one paradigm often becomes possible when viewed through another. To someone living in the 12th century, the idea of talking instantly to a person on the other side of the world would have sounded absurd. They would have called it magic. Today, we call it Wi-Fi. The principles that make it work were always there, hidden in the structure of reality. We just hadn't discovered how to harness them yet. The same may be true for interstellar travel. Perhaps there are dimensions of physics, energy, or reality that we have yet to uncover. Concepts like warp drives, wormholes, or quantum tunneling are speculative now, but they reflect our deep desire to find paths around the universe's limits rather than through them. They are not defiance of science. They are expressions of curiosity, hypotheses waiting for the tools of future generations to test. In that sense, impossible is less a verdict and more a snapshot of our ignorance. It tells us not what cannot be done, but what we cannot do yet. The boundaries of possibility expand as our knowledge does. Just as ancient astronomers believed the stars were fixed to a crystal dome above the Earth, we too may one day look back and laugh at how small our understanding of the cosmos once was. Yet the philosophical challenge of the impossible goes deeper than just optimism about the future. It asks us to confront our existential limitations, not just the limits of technology, but the limits of human life, patience, and perspective. We live at most a century. Our civilizations span a few thousand years. The universe is nearly 14 billion years old. Against such a backdrop, even the grandest human project can feel fleeting. So when we talk about traveling to another star, we are really asking whether meaning itself can survive across epochs. Can a species bound by mortality build a dream that transcends its own lifespan? This question forces us to reconsider what exploration means. If we cannot reach another star within a human lifetime, does that make the effort meaningless? Not necessarily. The value of exploration has never been measured solely in the arrival. When the ancient Polynesians set out across the Pacific, many of their journeys lasted generations. When medieval builders constructed cathedrals, they worked on projects that would not be finished until long after they were gone. They built not for themselves, but for the continuation of something greater, an act of faith in the endurance of purpose. Perhaps interstellar exploration will be the same. To say that going to Proxima Centauri is impossible is to judge it by the standards of the present. But the present is not the measure of eternity. 1,000 years from now, humanity, or whatever we have become, may look back at this era as the infancy of our cosmic story. They may view our spacecraft, our telescopes, and our debates about impossibility the way we view cave paintings, primitive but foundational. In that light, impossibility becomes a kind of invitation, a challenge whispered by the universe itself. You are not ready yet, but one day you might be. Philosophically, the word impossible also reflects a tension between humility and ambition. On one hand, it reminds us that we are small, tiny creatures clinging to a fragile planet in a vast, indifferent cosmos. On the other, it pushes us to strive, to reach, to imagine. Without impossibility, there would be no progress, because everything would already be known, already within reach. The existence of impossibility is the very fuel of discovery. It's what makes curiosity meaningful. In this sense, saying that a journey to Proxima Centauri is impossible today doesn't close the door, it opens it. It tells future generations, here lies a frontier. The act of naming what we cannot do yet defines the path of what we will someday attempt. The impossible marks the edge of the possible, and it is at that edge where humanity has always thrived. there's also an ethical and philosophical layer to consider. When we chase the impossible, we are also forced to ask why. Is it for glory? Knowledge? Survival? The dream of touching another star is not only a scientific quest, but a spiritual one. A search for meaning in a universe that offers no guarantees. Even if we never succeed, the striving itself becomes a statement of who we are. Beings who dare to hope, even when hope seems irrational. So perhaps impossible is not a wall, but a mirror. One that reflects back the limits of our courage, patience, and vision. It challenges us to see whether we are content with the boundaries we have or whether we will risk everything to expand them. And while we must recognize that some barriers, like the speed of light, may remain unbroken, there's a deeper truth beneath all of this. Impossibility is not static. It evolves with us. As we grow in knowledge and imagination, what was once unthinkable becomes inevitable. That is why, even if we cannot yet touch the stars, we continue to study them. Even if we cannot yet build a ship to Pluto or Proxima Centauri, we continue to imagine how we might. Because imagination itself is the first step toward possibility, the quiet rebellion against the word impossible. But philosophy alone cannot carry us forward. It can only inspire us to keep pushing. And indeed, as we move into the next stage of our exploration, there are signs that the impossible might someday become achievable. The breakthroughs in artificial intelligence, material science, propulsion research, and quantum physics unfolding today suggest that humanity is slowly, methodically, and irresistibly expanding the boundaries of the possible. That leads us into the next part of our reflection. An acknowledgement that even though we are far from the stars, the progress we are making today could one day bridge that immense divide. The impossible, after all, has a habit of becoming possible, one discovery at a time. Even as we reflect on the overwhelming challenges of distance, time, and physical law, there's a counterpoint that refuses to be silenced: the steady, unstoppable progress of human ingenuity. Every generation inherits the word impossible and chips away at it until it becomes merely improbable, then difficult, and eventually achieved. While traveling to Pluto or Proxima Centauri still lies far beyond our reach, the path toward that dream is being quietly paved in laboratories, observatories, and research centers across the world. The breakthroughs unfolding today in material science, artificial intelligence, propulsion technology, and quantum physics may not send us to the stars tomorrow, but they are rewriting the foundation of what might one day make such journeys feasible. Let's begin with material science, the silent backbone of every technological revolution. Space is the ultimate stress test for materials. Radiation, micrometeoroid impacts, extreme temperature swings, and vacuum conditions demand substances that can withstand conditions no earthly environment could replicate. In the past, the limits of our materials defined the limits of our exploration. The early space age relied on aluminum alloys. Later generations used titanium and carbon composites. But today, researchers are creating materials at the molecular and atomic scale, crafting substances that behave unlike anything found in nature.
One example is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. It's stronger than steel, lighter than aluminum, and conducts electricity and heat with extraordinary efficiency. If scaled and manufactured reliably, it could revolutionize spacecraft design, providing lighter, more durable hulls capable of withstanding cosmic radiation and micrometeoroid impacts. Beyond graphene, metamaterials, engineered substances that manipulate light and electromagnetic waves, could one day form radiation-resistant coatings or thermal shields that adapt dynamically to changing conditions in deep space. Even the dream of a self-healing spacecraft skin, capable of sealing micrometeoroid punctures automatically, is moving from science fiction to early experimental reality.
Advances in nanotechnology also hold promise for future spacecraft. Imagine services that clean themselves of dust, circuits that repair radiation damage on the molecular level, or materials that can change stiffness and flexibility depending on temperature or stress. These innovations are not just about strength, they're about longevity. A probe that can endure for centuries must not merely resist damage, it must recover from it. The next generation of spacecraft may not be passive objects, but active structures, continuously maintaining and evolving themselves as they traverse the void. Complementing this revolution in materials is the exponential progress in artificial intelligence. Any mission beyond the solar system would, by necessity, have to be autonomous. Communication delays spanning years or even decades make real-time control impossible. The spacecraft must think, adapt, and make decisions without waiting for human guidance. Modern AI is rapidly evolving toward that level of independence. Today's deep learning systems already interpret data from telescopes, navigate rovers on Mars, and manage complex spacecraft systems with minimal oversight. The next step will be AI capable of self-diagnosis, self-repair, and strategic planning, systems that can reprogram themselves in response to unforeseen situations. Imagine an interstellar probe encountering an unforeseen obstacle or malfunction. Rather than waiting centuries for instructions from Earth, it would analyze the problem, test solutions in virtual simulations, and fix itself using onboard tools or nanobots. In a sense, the ship would become its own captain, crew, and engineer, a self-sustaining intelligence built to outlast its creators. Some visionaries even speculate about AI-driven civilizations of machines, networks of intelligent probes spreading through the galaxy, learning, adapting, and sending data back across millennia. It's a concept known as von Neumann probes, after the mathematician John von Neumann, who proposed the idea of self-replicating machines. Such probes could, in theory, reproduce themselves using local materials, turning asteroids into factories and spreading outward in an ever-growing wave of exploration. While that remains theoretical, the idea underlines an essential truth. If humanity cannot cross the stars biologically, it may do so digitally. Our descendants may not be flesh and blood explorers, but intelligent machines carrying our legacy forward. Meanwhile, progress in propulsion technology continues at a pace that, while not yet interstellar, is undeniably accelerating. NASA, private companies, and international agencies are investing heavily in nuclear thermal and nuclear electric propulsion, systems that could drastically reduce travel times within the solar system. The VASIMIR, or Variable Specific Impulse Magnetoplasma rocket, uses plasma and magnetic fields to achieve efficient continuous thrust. It could cut the trip to Mars from months to weeks, a major leap forward in sustainable deep space travel. Beyond nuclear propulsion, experimental concepts like fusion drives are moving from theoretical papers into laboratory prototypes. Projects like the Direct Fusion Drive at Princeton Plasma Physics Laboratory aim to create compact fusion engines that generate both thrust and electrical power. If successful, such systems could open the door to travel speeds that make the outer solar system, including Pluto, far more accessible. While we're still far from the dream of reaching another star, each advancement in propulsion is a step toward faster, more efficient exploration. At the same time, laser propulsion, particularly the concept of light sails, is gaining serious attention. The Breakthrough Starshot initiative, led by physicist Stephen Hawking and investor Yuri Milner, has already begun experimental work on miniature spacecraft propelled by powerful Earth-based lasers. Though the project faces massive technical challenges, it represents a crucial shift in thinking, that propulsion doesn't have to come from fuel carried on board. Instead, it can be beamed from afar, allowing craft to travel light and fast. This concept, if scaled, could transform the physics of interstellar missions.
There's also promising progress in energy storage and generation. Advances in compact fusion reactors, radioisotope thermoelectric generators, RTGs, and high-efficiency solar collection systems could make future missions vastly more self-sufficient. Even quantum energy harvesting, a frontier still in its infancy, hints at the possibility of extracting usable energy from vacuum fluctuations, a concept that, if realized, would utterly revolutionize deep space travel. And then there's quantum communication and computing. While real-time communication across light years remains impossible,
quantum entanglement research is revealing strange, potentially transformative ways of linking information across space. Although we cannot yet use entanglement to transmit messages faster than light, quantum technologies could enable ultra-secure, interference-resistant communication systems capable of surviving the rigors of interstellar distance. Quantum computers, too, could allow spacecraft to process immense amounts of navigational and environmental data efficiently, optimizing every watt of energy and every gram of fuel. Taken together, these developments suggest something profound. The impossible is shrinking. The gaps between what we dream and what we can do are narrowing step by step. No single discovery will make interstellar travel feasible overnight, but the accumulation of progress across hundreds of disciplines may one day converge into a moment when the idea no longer sounds like fantasy. Even the human factor, our biology and psychology, is seeing progress that might one day complement these technological advances. Research into cryogenics, hibernation, and longevity may make it possible for humans to sleep through long journeys or extend their lives enough to see missions completed. Advances in biotechnology and genetic engineering could one day produce humans capable of withstanding radiation and zero gravity better than we can today. It's not just about building better machines, it's about evolving the explorers themselves. Of course, all of this remains speculative to some degree. We are still bound to our solar system, still limited by the speed of light, still fragile creatures of a small blue planet. But to look at the trajectory of human progress is to see a pattern that repeats across history. Every boundary we encounter becomes the foundation for the next leap forward. The same minds that once looked up and wondered if the moon was reachable now send robotic emissaries to the edges of the solar system. The same curiosity that invented flight now probes the very fabric of space-time. So while it remains impossible for now to travel to Pluto or to cross the Gulf to Proxima Centauri, it is equally true that the impossible of yesterday has always been the achievement of tomorrow. The story of humanity is the story of persistent acceleration, of knowledge compounding, tools evolving, and imagination outpacing despair. And perhaps that is the ultimate reason to hope. We may not yet possess the engines or the endurance to sail the stars, but every equation solved, every probe launched, every new alloy, algorithm, and experiment brings us a fraction closer to the day when impossible will once again be rewritten. Still, amid this growing optimism, it's important to retain perspective. Even if technology eventually allows us to breach the cosmic frontier, the journey will take so long that it will reshape not only our science, but our civilization itself. Before we can truly go outward, we must understand who we are inwardly and why the urge to explore drives us so deeply. That reflection brings us to our final segment, a moment to step back, look at all we've learned, and remember that even if we cannot yet touch the stars, the very act of reaching for them has already transformed us. In the end, the question of why it's impossible to travel to Pluto or Proxima Centauri isn't really a story of defeat. It's a mirror held up to the boundaries of our current understanding. It's a reminder of how small we still are in a universe that is vast beyond imagination, and yet how far we've already come for a species that once looked up at the night sky and thought the stars were pinpricks in a celestial dome. The truth is, our inability to reach these distant worlds today isn't a failure of ambition. It's a testament to the scale of the challenge, to the sheer immensity of space, and the humility it demands of us. But it is also, paradoxically, a source of inspiration, because understanding our limits is the first step towards transcending them.
When we think of Pluto, that cold, distant dwarf planet orbiting in the outer reaches of our solar system, we're reminded that humanity already has touched the edge of what once seemed unreachable. In 2015, the New Horizons spacecraft captured stunning images of Pluto's icy plains and heart-shaped surface, revealing a world more complex and beautiful than anyone imagined. That mission took nearly a decade, crossing billions of kilometers, powered by a tiny plutonium generator and guided by the patience of human curiosity. It was a humbling success story, one that proved persistence could turn impossibility into achievement, step by step, year by year. Proxima Centauri, by contrast, stands as a symbol of the ultimate frontier, a beacon of hope and challenge, a reminder that there will always be another horizon to chase. We may not reach it in our lifetimes, or even in the lifetime of our civilization as it exists now, but it continues to call to us. Every time a telescope captures a flare from that small red star, or a hint of an exoplanet orbiting within its habitable zone, we're reminded that the cosmos is not empty. It's alive with possibilities. And even though those possibilities lie light years away, the act of striving to understand them connects us more deeply to the universe than ever before. It's important to see this not as a wall, but as a staircase, one whose steps are built from knowledge, imagination, and determination. Each new discovery in physics, propulsion, or artificial intelligence is a rung upward. Even if the summit, the day when humans or our robotic descendants set course for another star, remains far away, every step taken toward it enriches life here on Earth. The research that pushes the boundaries of deep space travel also improves medicine, computing, materials, and our understanding of energy. In reaching outward, we advance inward, refining what it means to be intelligent, creative beings in a vast and mysterious cosmos. There's also a quiet, profound truth in recognizing our limitations. Knowing that light takes over 4 years to reach Proxima Centauri, that our fastest probes would need tens of thousands of years to get there, and that the energy required for interstellar travel is beyond our reach, this knowledge grounds us. It teaches us patience. It gives us perspective on time, on progress, on the delicate fragility of our moment in the universe. It reminds us that our planet, this pale blue dot, is not just our home, but our shared vessel in an ocean so immense that, for now, we can only sail near its shores. But history has shown that every great human achievement begins with a recognition of limitation. The dream of flight was once dismissed as fantasy. The idea of landing on the moon was once a fairy tale. Yet in less than a century, both became reality. What separates the impossible from the possible is time, and the relentless drive of human curiosity. So while today we can't reach Pluto easily, and Proxima Centauri may as well be an unreachable dream, tomorrow's generations may look back on our struggles and see them as the first glimmers of a journey that eventually took humanity to the stars. In that sense, the word impossible doesn't signify an ending. It marks a beginning. It's the starting line of every great discovery. Each no spoken by physics or engineering is an invitation to ask how. Each failed test, each unsolved equation, each obstacle in space exploration is a whisper urging us to try again, to think differently, to imagine further. So while we stand here, gazing across the void at Pluto's icy plains and Proxima Centauri's faint red glow, we should not feel small. We should feel privileged. Privileged to be conscious beings capable of understanding the scale of the universe and daring to dream of crossing it. The fact that we can even define the problem, calculate the distances, imagine the physics, map the stars, means we have already taken the first step towards solving it. The universe is vast, yes, and our reach is small. But every technological leap, every act of exploration is a light in the dark. Proof that even in an infinite cosmos, intelligence and will can leave a mark. The impossible isn't permanent. It's simply waiting for the right moment in history, the right mind, the right spark. So let us keep looking upward, not with frustration at what we cannot yet do, but with gratitude for how far we've come and excitement for what lies ahead. Because one day, maybe not soon, maybe not even in 1,000 years, someone will look back at the early 21st century and say, this was when it began. This was when humanity first truly understood its limits and decided to surpass them. And until that day, we continue to explore, to learn, to imagine, not because it's easy or even possible right now, but because that is who we are. We are the species that dreams of touching the stars. And someday, whether through metal, mind, or memory, we will. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.